Okay, so last week we defined what it meant for something to be classical, and we defined this thing called the Bell polytope, um, which was basically just the set of all non-signaling distributions that could be derived from a joint probability distribution. Um, Okay, so a lot of people have heard of Bell inequalities. And so this week, what we want to basically talk about is how to formalize what a Bell inequality is. There's different kinds: trivial, non-trivial, tight, those that are not tight. And the basic idea is maybe something like this. Last time we defined, so first I will start with a sort of geometric picture, which is the following. So the Bell polytope that we defined last time is some geometric object, perhaps like this. The corners or vertices of this thing are precisely our d zeros. And one thing that we've talked about before is that there are non-signaling distributions, for example, those coming from quantum mechanics, that can lie outside. So this is a non-signaling distribution. And so if I have something in here, then this thing will be called classical or local. And the ones that are outside are going to be non-local. So how do we witness these? Well, these turn out to be precisely Bell inequalities. So a Bell inequality is going to be maybe something like this. It's any inequality. So an inequality that splits the space into three pieces: those that are directly on this line, those that are on the other side of this line, and those are in this side. So a Bell inequality is any inequality such that the Bell polytope is on the one side of it. So there can be trivial Bell inequalities, ones like, oh, the probabilities in my experiment are non-negative. Those can be trivial. And there can be ones that are tight and non-tight. So a Bell inequality just requires that all of the, for example, classical distributions lie on one side of it. But you can see here that there are distributions that are non-local or non-classical, P prime, which might be still inside of this. So this inequality here might not necessarily witness that this is non-classical, even though it is. So we will say that a Bell inequality is tight if it corresponds to one of these inequalities here that define the polytope itself. So we'll make this more precise as we go, but this is the rough geometric picture. There are Bell inequalities, anything for which the Bell polytope lies on one side of it, and then there's the ones that are tight, which is to say that a distribution is non-classical or non-local if and only if it violates one of these. So let's just recall a little bit what we did last time. So just a little bit of review. We said that something, a joint probability distribution, is something that we can write like this: O prime as a convex mixture of deterministic distributions, and that this induces or just from here, you can always derive a corresponding non-signaling distribution P, where these convex coefficients are precisely the same as these, and this is the non-signaling distribution corresponding to this deterministic joint probability distribution. So this is a joint probability distribution, and this is the corresponding non-signaling distribution. We could also think of, we tried to think of these P's as also maybe being like convex mixtures of these tables of 16 numbers. So that's another equivalent, maybe more concrete way to think about it. In particular, we have that P, if P is of this form, then it's also in L, where L, we said, was the convex hull of D zeros, like this. So something is in this polytope if and only if it's of this form. So we also said the following. Are equivalent. The following are equivalent. We have P is so classical or local. P is in L, or there exists a joint probability distribution actually, yeah, and that's what I wanted to say about this. So the question, which I sort of previewed the answer for, is the following. How can we So, how can we witness if a particular P is non-classical or non-local? So the answer to this is precisely as I was sort of previewing here. Is that we have Bell inequalities. So how are we going to actually derive these Bell inequalities? Okay, so non-locality. Okay, non-locality witnesses. So first, what we want to do is we want to think of these as being concretely in some Rn. So we want to think of, consider that D0 is in Rn. Here we're considering the CHSH scenario, so n is equal to 16. So this is the number of empirical probabilities in our scenario. And what we want to do is define a matrix as such equals whose columns are precisely these D zeros. So D01 all the way to D0K. Here we have that K equals 16 is the number of global value assignments. So these are the number of possible tuples you have over your set of measurements. Recall that what we're saying is a joint or a global outcome assignment is I'm taking each of my possible measurements. So Alice has 2 measurements, Bob has 2 measurements, and we're assigning a bit or a 0 or 1 to each of these. So there's 16 possible deterministic global assignments. And that's where the K equals 16 is coming from. This is 2 to the 4. Actually, let's continue like this then. So here I labeled these 1 to 16. So each 0I is some particular set of zeros and ones. 0, I, A0, 1, I, A1, 0, I, A1, 1, I. Which is basically what I was saying before. And also, let Q tilde equal Q1 all the way to QK in RK. So, what I want to replicate is a formula that looks like this. This thing has some real coefficients, non-negative in this case, but what you see is that you have a sum over some vectors. So what I want to replicate is a matrix multiplication. I have these as my columns. And what I'm going to do is, by matrix multiplication, we obtain gives us some well, not necessarily a non-signaling distribution, but just from matrix multiplication, we have a vector in R16, which is given by M times Q tilde. So in general, this can just be arbitrary real coefficients. Nothing so far actually connects us to this case. But to connect to this case, what do we actually need? We need to make sure that these are non-negative, and we also need to make sure that this is normalized. So we need the additional constraints. The first one being that we need the Qi to be greater than 0 for every I. Okay, and second, we also need that the sum of Qi is equal to 1. So in order to, well, we want still a sort of nice linear algebraic sort of formula. So I'm going to introduce, so this additional constraint here is going to be a little bit tricky. So what I'm going to do is introduce an additional coordinate, and you'll see that once we introduce that coordinate, you can guarantee this normalization automatically. So maybe go over here. So the idea is the following. For any v in Rn, we define the vector vh, which has got 1 on the additional coordinate, and then v for the rest of it. And this is in R nh, I'll call it. Nh is just n plus 1. So it's 17 in our specific case, but this is a completely general thing to do. One thing that's sort of nice about this is many of the computer programs they use to perform these types of calculations, they always introduce a homogenizing coordinate. The 1 there means that you actually have a vertex of your polytope, and if it's 0, you have what's called a ray, which means that it actually is infinite, and it's sort of just think of like coordinate axes. So it's sort of good best practice to include this homogenizing coordinate in general, but it's a convention. So, for example, if I have some non-signaling distribution, I can map this to its homogenized version, which is 1p in R of nh. Similarly, so this is the general case, so of course we can also define the deterministic ones in the same way. 1 d0. So now what does our matrix multiplication look like? Well, maybe what we will do is first write down this matrix, the homogenized version, which is just going to be d0h, d01, 0k, h. What is this doing? Essentially, it's the same matrix as I have here, but with an additional row of 1s appended on top. So this is just something like a row of 1s transposed m, something like that. And now what we want to actually satisfy, so something is going to be classical if I can solve the following linear system. P is in L if there exists a solution to the linear system. So P in L, if and only if there we have PH equals MHQ tilde. All right, did I use tilde before? Yes. Tilde such that Q tilde is greater than or equal to 0. Note that so let's rewrite this a little bit. So we have 1p equals, what is this? These columns are precisely this, so you will get something that looks like sum I equals 1 to 16 qi tilde of 1 d0. Now, a solution to this problem would precisely require that First of all, I'm going to require that these are non-negative, but then also that the sum of these things on the zeroth component, I'll call it the zeroth component, has to equal 1, which is precisely the normalization. So we have that P is an L if and only if this system holds, because this system is precisely telling us whether there's a joint probability distribution over the global outcome assignments such that this holds. So, okay. Let's chew on that for a moment. Okay, so let's define what a Bell inequality is in a little bit more detail. So we say that some W in R and H in 17 dimensions, that is a Bell inequality maybe sometimes I will just abbreviate it as BI is a Bell inequality if we have dW transpose DOH greater than 0 for every O in O. Which is the same thing as saying W transpose acting on MH greater than or equal to the 0 operator or vector on, let's see how many. There should be k of these. So the k-dimensional 0 vector transposed. That's just saying the same thing. Okay, let's actually go a little bit further with this. So what is this saying? So maybe you're a little bit uncomfortable with these h's, what's going on here. So we can just say that W can be equal to some minus alpha. This is just a convention. And A in R and H. So I'm just splitting up this 0 homogenizing coordinate and A. And what I'm saying essentially is that what is this inequality? It's WT acting on any D0. H is going to be precisely minus alpha because here I have an extra 1 coordinate which just hits this alpha. So I get minus alpha plus A transpose D0 greater than 0 or just A transpose D greater than alpha. So we say that something is a Bell inequality if there is some vector A such that all D zeros are greater than or equal to some alpha. I want to say that why have I just restricted to the D zeros? Well, it's the case that if it's the case that it's satisfied by all D zeros, then it will be satisfied for all local distributions. So how can we see that? Consider the following. If we have that pH is equal to some D0H, then when we do W transpose on pH, this is going to be equal to some O and O, P of O, W transpose D0 of H. Now, the inequality in this form is a little bit easier to see. It's got to be greater than or equal to 0. I'm saying that if this is satisfied for all D zeros, well, this is non-negative, and these are non-negative. Therefore, this must also be non-negative. So it suffices just to consider, we just need to check how it acts on the vertices. And we'll see that this theme sort of recurs later on. A sort of remark. One of them is, or just in general, Bell inequalities can be trivial. So what does that mean? Well, there's a couple of sort of important examples. I don't know how important they are, but these are sort of just straightforward. What if you have that W is equal to the 0 vector? Well, then, of course, W transpose of any vector V, but including DO, H will be greater than or equal to, well, maybe make this will be 0, which is obviously greater than or equal to 0. So you can have that Bell inequalities can in fact be trivial. Another one, I will just say this maybe without sort of trying to formalize it, but you could imagine that there's a way to use these W's to say the following, that my empirical probabilities are greater than 0. You can connect it to this W in the following way. If you let S comma X correspond to a particular I in 1 to n, so basically I'm saying that let me take all the possible probabilities, they're indexed by these S's and X's, and then just sort of order them from 1 to 16, and let this be one of them. So then this inequality is going to be precisely if W is equal to 0, comma, the unit vector corresponding to I. So then you will have W transpose on P homogenize is going to be equal to saying that Pi is greater than 0. So this one is also trivial in the sense that anything that we consider a non-signaling distribution should already satisfy this. Okay, so how can one generate these inequalities, these Bell inequalities, or where do they come from? One sort of, and indeed there's an additional question. I mean, from the geometry, it's kind of clear, the one that I drew before, that you either have this case where it seems obvious, at least, that either something is on one side of this inequality and therefore is a Bell inequality, or it doesn't satisfy it. So what can we make this a little bit more rigorous? And in fact, we can. There's Farkas's lemma. We won't prove it, but it's a standard result in optimization theory and or convex geometry, but it's just basically saying the following, and we'll see the connection to our Bell scenario case. So let V be a matrix, n by m, and B be some R n. Then one of two situations must hold. Either there exists a Q in Rm such that VQ is equal to B for Q greater than or equal to 0, or 2, there exists a W in Rn such that this is again interpreted as a suitable vector. Maybe it's transpose. Let's see. What does the dimension of this have to be? 1 by, so this is the 0 vector in m dimensions and transposed. Okay, so what is Farkas's lemma telling us? So if you have a matrix and some vector b, then there either exists a Q such that this holds, or there exists, so basically what is this? This is precisely of the form that we're saying. Either there's a non-negative combination, a non-negative set of coefficients such that this holds, or there must exist some vector such that all the columns of V satisfy this equation, that is, they're greater than or equal to 0, whereas the inner product with B itself must be less than 0. That is, there must exist some inequality which separates or witnesses the separation of B from sort of like the convex hull of the columns of this vector. So in our situation, what does this correspond to? Clearly, it seems like, and I'll just write it down in a second, either you have the case that something is classical, that this solution holds, or this happens. And so the reason for introducing Farkas' lemma is just to really confirm that these are really the only cases that can happen. From the geometry, it's somewhat clear, but it's good to just make sure that you have a strong theoretical result behind that. So let's just so in our case, we have the following. N equals N, K equals to M, and big M is equal to V, and PH equals to B. So when we apply Farkas's lemma, we have one of two cases. Either something is classical, that is, there exists coefficients Q such that equals PH, where Q greater than Z. So this is precisely what we were saying before as something being classical, that is to say that P is in L, or we have something is non-classical in the sense that there exists W in R in H such that and this is the non-classical case. And the geometry is precisely such as what I was talking about before. You have this. So this is our set L of classical distributions. It also helps to think that there's actually a bigger set here. This is the set of all non-signaling distributions. These are the vertices of this thing. And these are our D zeros. So, and a Bell inequality. So precisely we have one of two situations. Either P is here and there exists some inequality which witnesses that, so that it's on the wrong side of it, and the L is on the right side of it, or it's in here and there exists some set of Q's, a joint probability distribution, precisely so that it falls right in here. Okay, so we want to return to our discussion of Bell inequalities with these very important ones, tight Bell inequalities. Sorry. Okay, so what is the importance of tight Bell inequalities? So we pose the following question. For which Bell inequalities does the following hold? In particular, say we have an inequality that WT is greater than or equal to 0 for sure. Okay, so there's a bit of a subtlety here, but just we'll discuss that in a moment. For sure implies, or let's see, maybe the other direction makes more sense. Sorry, okay, this on its own is not sufficient, but so what we want to say, and I will explain the subtlety in a second, that satisfying this inequality implies, so let's put some quotations around this, that P is in L. the geometric picture is precisely the one that I drew before. The reason that this is not sufficient is, and you'll see it from the picture, is that I could have, so the type Bell inequalities, the one that I'm going to reference and make a little bit more rigorous in a second, are precisely the ones that hug the boundaries of this object, right? So these are going to be the type Bell inequalities. But of course, this is not sufficient. What you really want to say is that there's a collection of W's such that if this is satisfied, so maybe it's more like a collection of these, such that if all of these are satisfied, you know that P is inside of this polytope. Because as it is, with a single one, you could have something here, which is on the correct side, but it's not on the correct side of also this one. So you have to be a little bit careful. But the idea of the type Bell inequalities are precisely that collection of inequalities for which satisfying these tells you precisely that P is inside of this polytope. So the answer is that these are the facets of the Bell polytope, which we said was L. So in order to really understand what this is, in particular what this idea of facet is, we'll need to sort of recall some basic polytope theory. Okay, so, and we're going to try and give some basic examples to make all of this a little bit more intuitive. So let P be a subset of Rn, be a D, note that N and D do not have to be the same. D obviously has to be, or N has to be greater than or equal to D, but sometimes, like in our case, when you think of the non-signaling or the Bell polytope concretely in R16, we had discussed last time that actually these polytopes are in a lower dimension, 8 dimensions. If you recall, there are these expectation values, the local expectations for each of Alice and Bob's measurements, and then their correlations, so 8 altogether. So I deliberately sort of want to emphasize that I could think of this polytope as being a proper subset of some Rn, but it need not be n-dimensional, it can be d-dimensional. So if a d-dimensional polytope is in Rd, we call it full dimensional. So that's, you can sort of always restrict to that case, but let's just sort of keep them distinct for now. So if we have this d-dimensional object, then we say a face, we say a subset F of P is a face if F is equal to, so bear with me for a second, it's Rn B. Okay, so let's unpack this. What is this? This is precisely an affine hyperplane. Basically, I'm saying that a face is any time you take something that's an affine hyperplane of some dimension and you cut the polytope with it, but also there's an additional ingredient, and this is important, such that B transpose Y greater than beta for every y in P. So let's give a little example of what's going on here. So the idea is to look at the cube in R3. So I'll just draw it. And it will be nice to have some colors to play with. So it will be, let's set the origin to be at the barycenter of this cube. So we can think of this as having sides of length 2, 0 to +1, 0 to -1 in every direction. And let's think of the following. Okay, so a coordinate u in R3, some vector, will be given by x, y, z transpose in R3. Now what I want to do is to give you an example of faces. These can be of different dimensions depending on the dimension of the affine hyperplane that this guy sort of details. So let's see what that sort of looks like. So you can have, in this case, a two-dimensional face. What does the two-dimensional face correspond to? Well, by the way, so the faces here can be of different dimensions, and they can include P itself. So if for example, this is 0 and this is 0, then everything of course satisfies it. So the polytope itself can always be a face. And then you can have the next highest dimensional. Those are going to be called the facets. That's what we're interested in. So in this case, I have the two-dimensional face. Where is that coming from? Well, it's precisely the facet so the two-dimensional case is going to be given precisely by the inequality z is greater than or equal to -1. In this case, you have that B transpose is equal to 0, 0, 1. And then you have that beta equals -1. Okay, very good. So what about the one-dimensional case? So here, a one-dimensional face should be precisely, maybe it's worth getting a different color. A one-dimensional face is going to be something like an edge, which I've tried to draw here in blue. So the one-dimensional face is going to be something like, I can actually generate them like this, hopefully. So y greater than or equal to -1 plus, so I'm adding two inequalities. So in order to actually get something that's lower dimension, these facets basically determine membership in this object. That's why we're going to be interested in the facets. And if you want the lower dimensional faces, you can actually add the facets together. So that's one way of generating the inequalities for the lower dimensional faces. So if I add y greater than or equal to -1, that's me specifying everything is on this side. Sorry, hold on. Y greater than or equal to -1 is this way. So actually, I think I will be, perhaps I should think this is not correct. It's not this top face. Z greater than or equal to -1 is this. So this should be white. And then if I do y greater than or equal to -1 plus z greater than or equal to -1, this is equal to y plus z greater than or equal to -2. So that is precisely this face. You see that everything on this line, this is precisely the line on which, so for the two-dimensional case, we have that this plane here, the bottom face of the cube, is precisely all the points such that their z coordinate is -1. So now, if you go to the one-dimensional case, it's all of the points in this cube such that their coordinates are, their y coordinate is -1, their z coordinate is -1, and there's a one-dimensional line that satisfies this. Precisely those such that y plus z is equal to -2. And you can even have zero-dimensional faces. This is going to be y greater, so maybe start in order. As you might expect, negative x greater than or equal to -1 plus y greater than or equal to -1 plus z greater than or equal to -1. This is going to be x plus y plus z greater than or equal to -3. Now there's precisely only one point that satisfies that inequality, because these are all the collection of points such that their sum is -3. Here you have the point -1, -1, -1, and that's precisely a unique solution and a vertex. So this is your zero-dimensional one. And so you can sort of see the pattern of how these are going. Of course, the three-dimensional one is P itself, as I mentioned. In general, we have that face F or P is a facet if dimension of F equals D minus 1. And the corresponding inequality, we say the corresponding inequality is called facet defining. Say, sorry, wrong. A transpose x greater than or equal to alpha is called facet defining. So, we will sort of state without proving. There is also this result and that is the following. P in Rn is P is equal to the convex hull of a finite set of vectors if and only if it's also, so I will try and write it like this. It is the collection of points. So if and only if P is also equal to the intersection K equals 1 to, or let's just say over K of X element of Rn such that B K transpose X greater than or equal to beta K. So, and there's finitely many of these. So we have something that's called a convex polytope. So it's either the probabilistic mixture of a finite set of points, or it's the intersection of a finite number of half-space inequalities or facet-defining inequalities. So this is like the fundamental theorem of polytope theory. So basically, we have that in our case, we have that L is given as the convex hull of these deterministic non-signaling distributions. But it's also equal to the intersection over, let's just say, K of these Bell inequalities, half spaces. So let's just call these, say, BK. And basically, these are two dual different kinds of problems. If you want to know whether a point is inside of L or not, it's really good to have this, because then you can just check, I have these inequalities, and I just check each of the inequalities. This is good for other practical purposes, different kinds of problems. You might want what is called, this is called the V representation for vertex. This is called the H representation. Okay, but so say that we want to find these facets. I have not really described to you how to, in this case, it's very easy to find the facets. You basically just geometrically can pick them out. But what is the sort of strategy for actually computing these? So we have the following problem. Given the V representation, which is often, in polytope theory, you often have one of these or the other, and converting between them is, in general, a hard problem. So if you have the V representation, you might want to find the facets, and how do you do that? Or if you have the facets, how do you find the vertices? So geometrically, we sort of see, I think it's a little bit easier to go from the facets to the vertices, because what's happening there? If you look at what are the vertices, these are precisely where three of the facets in this case, they intersect. So you can think of a vertex. Vertex equals a unique solution to a system of equations. So I take three of my facets and I look at the collection of points that satisfy these facets with perfect equality. And that's precisely and this solution, if the solution is inside of the polytope, then you have that it's a vertex of the polytope. So you see that there is a sort of maybe a brute force mechanism or a brute force strategy you could use for generating these vertices, which is I'm going to look for all the sort of linearly independent facets and then look for their solutions and then just check to see if those solutions are inside the polytope or not. That's maybe not the best, it turns out not to be the best strategy because there's many different ways I mean, from the cube, it's hard to see, but in general, you will actually have the case that there's many different subsets of these facets, which could be linearly independent and therefore give you a unique solution. So you in general have to be a little bit more clever than that. We will not right now go through some of these more clever strategies, but there are ways that people have talked about. One is, say you're at one vertex here, and you want to generate all the vertices. What you do is you sort of say, okay, I'm going to fix d minus one of these to stay the same and relax one of the inequalities so I can vary it. And then I go to the neighbor. And then I go to the neighbor. So this is a pivoting strategy. And it works quite well in practice, but there are going to be cases where this thing fails. In particular, it's hard to see from this one, but if you have a polytope where it's the solution, it's the unique solution to more than one choice of three facets. So then you can do this thing called cycling. So here you could choose, if I have this little Egyptian pyramid on top of this, I can choose 1, 2, 3 of these facets and get this unique solution up here. But there's 4 facets up top, and actually I could relax one of these and then let the algorithm go, and then it could bring me back to the same exact one. So this is called cycling, and so that's the downside of this one. There's another strategy where you sort of instead of pivoting in the way that I've described, you sort of take a initial block and then you like sculpt it by cutting off with certain facets. And that also has a certain problem, which is as you cut through it, you generate new kinds of vertices, and there's a lot of intermediate vertices, which are not the vertices of the polytope that you want. And there's this sort of exponential blow up in the middle. Maybe we'll talk about that in a later lecture. But suffice to say that there are some additional strategies. But for our purposes, we have the V representation, and then we want the H representation. It turns out that the way of getting these facets is not altogether different. In fact, the problems are like dual to each other. You still have to solve a system of linear equations to get the facets. So we'll see how that works. But so, given the V representation, how to compute the facets I dot E, the H representation. This is also called the facet enumeration problem. Okay, so let's see if I will have enough room to put it here. I will go here. Oh no. Hidden. Okay. Okay, so we're going to need to have a more algorithmic sort of definition of a facet in order for us to figure out how to compute these tight inequalities or these facets. I will just sort of lay out the definition and give some other examples. In practice, this is quite a tedious task, and doing it by hand is almost very rarely is it practical to do by hand. So let P be given as the convex hull of a finite set of points. So this is the V representation. Be d-dimensional convex polytope, a subset f of p is a facet if and only if there exists alpha in R and A in Rn such that, hopefully this will not be too bad to see. One is that there exists D affinely independent vertices vi1, vid in P such that AT VIK greater than, equals alpha for all k equals 1 to D, and 2, that A transpose X greater than alpha for every X in P. Okay, so let's unpack this. This is a little bit much, but just to give you a flavor of where things are going, essentially the D affinely independent vertices. I mean, this is a system of linear equations, and the fact that these are affinely independent is basically going to tell us that we can solve this up to some overall factor, which will become important in determining the second piece. In general, this first piece will just give you the vector AT and alpha up to some overall constant, and then that overall constant being positive or negative is going to tell you whether exactly what direction or how this inequality should go. To make sure that you pick it correctly, you need this freedom, this global scale factor, so that you can choose it in the direction such that P lies on the correct side. So let's build up some intuition for this. Actually, we already have the cube here, so why don't we? Okay, so in fact, we will just go back and use this cube example. Okay, just the cube. And now we're going to find the facets of this cube in a more direct fashion, instead of just inspection geometrically. So what we're going to do is we're going to look for a set of affinely independent vertices, and then we are going to solve this system of equations and see how the inequalities come up. So at first, why don't we define our vertices in this way: -1 to the Q, -1 to the R, -1 to the S, transpose in R3. I mean, our vertices are precisely all combinations of plus or minus 1 and R3, so there's 8 of them. That's what I've written here. And then we just have that the cube is going to be the convex hull of VQRS over all QRS. Now, consider a particular subset V000, V010, V100, V110. These are precisely the vectors that are on here. We can see geometrically that, in fact, they are all on this top facet. And so if you notice, they all have their S value being 0, so that it's on the plus 1z. Clearly, they're not all, these are not affinely independent. In fact, you have the following. V110 is equal to V010 plus V100 minus V000. This is, in fact, an affine combination, coefficient 1 plus 1, 2, minus 1, 1. So this is V110 is in the affine hull of the rest of them. And then you can check, actually, that these are, in fact, affinely independent. You just have something like this. Now, we're going to go ahead and solve this system of equations. So maybe it helps to... okay, let's use this a little bit. So let's go ahead and let my vector A be given by AX, AY, AZ transpose. Alpha will be just some real number. So what do we have? From the 0, 0, 0 case, we have that, AX plus AY plus AZ equals to alpha. 0, 1, 0 case, AX minus AY plus AZ equals alpha. 1, 0, 0 case, minus AX plus AY minus, plus AY, AZ equals alpha. If you add these two together, you get alpha Z equals alpha, AZ equals alpha. And if you add, for example, these two together, these are going to cancel out. This cancels out. AX equals 0. And then if I add, for example, these two together, then I also get AX equals AY equals 0, so that my inequality is going to be precisely for any U in R3, I have, and say that this is equal to X, Y, Z, then this A transpose U is going to be equal to, and let's say this is equal to some, or just keep it as alpha. So this is going to be precisely alpha Z equals to alpha. And now we need to decide whether alpha is positive or negative. In particular, what we need is A transpose U greater than or equal to alpha. So this is equal to alpha Z greater than or equal to alpha. So depending on the choice of sign for alpha, we could either get Z is greater than or equal to something, or Z is less than or equal to something. So let's consider those two cases. So if alpha is equal to alpha, then we have alpha Z greater than or equal to alpha, When we divide by alpha on both sides, we get z greater than or equal to 1. Z greater than or equal to 1 tells me I keep this slice and everything above it. That doesn't seem right geometrically. You have alpha is equal to minus alpha. So you have minus alpha z greater than or equal to minus alpha. When you divide on both sides, you have to flip. So z less than or equal to 1, which is precisely the direction that we want. So just to finish off having a little bit of intuition for how these things work, we can also see that there are some affinely independent sets which do not yield a facet. This is why we have to be a little bit clever. So let's continue on. What about the following set of vectors? 0, 0, v of 0, 1, 0, and v of 1, 1, 0. So which vectors are those? That's 0, 0, 0, 0, 1, 0. I'm saying that the y1 is back here, so that's this, 0, 1, 0. And then I have this all the way back here. So clearly, the convex hull of these things is going to be cutting through this. So geometrically, what we can sort of see is that when you define the vectors that you're going to look to see if they form a facet, the idea is that you can find a affinely independent set, like the original one that we looked at, and their convex hull should give you something that hugs the polytope. Here, we're going to see that it slices it. So, similar to before, we have ax, ay, az, and R3. So now our system of equations is going to be something like ax plus ay plus az equals alpha, ax minus ay plus az equals alpha, minus ax minus ay minus az, sorry, this should be 1, 1, 1, minus az equals alpha. Without spending too much time on this, what you end up getting is precisely that ax equals minus ay and az equals alpha equals 0. Let me make sure that that's correct. So the inequalities are going to look something like u are going to be x, sorry. And let's say that this is equal to some lambda. So we have lambda x minus lambda y greater than or equal to 0. Now what that means is lambda x is greater than or equal to lambda y. And the choice of sign for lambda is going to tell us what direction this inequality goes. But we can already see that this is going to violate certain vertices. So what this is saying is in one of the cases, so for lambda greater, let's say, just do the, we have x greater than or equal to y. What does that rule out? That says that that rules out, for example, it should rule out x greater than or equal to y. So if we have ones where x is less than y, it will rule those out. So anything on this side over here, let's see, did I do this correctly? X minus y greater than or equal to 0. So if x is less than y, oh yeah, right here. So here you have the point 1 parameterized by 1, 0, 0. Here x is minus 1, y is plus 1. This is clearly inside the cube, but this tells me it's not allowed. On the other hand, if I have that lambda is equal to minus, then you get x less than or equal to y. But then you have the opposite problem. You have stuff like this is violated. So clearly there's some additional strategy here, but algorithmically, this is how you actually determine the Bell inequalities. And in general, it's quite an intensive task. So for our case, we have 16 vectors in R16, and now you have to look at all the different combinations in principle to see which one of these give you the Bell facets that you want. Okay, so I think that we will look into this a little bit more in the homework, where we can have the aid of some computer software packages to help us do this.